Hello, everyone, and welcome to today's webinar. My name is Jennifer Caveney, and I will be moderating today's presentation. All right, so let's go ahead and get started. Our speaker today is Cosmin Belichu. He brings over 15 years of food industry experience in product development, working at all phases of product development cycle to bring products from concept to commercialization. In his current role as project leader with the National Food Lab in Ithaca, New York, he scopes and executes development projects to support our clients across the food and beverage industries. Cosmin is an active member of multiple trade associations and has authored many publications and scientific presentations. Cosmin, I'll hand it over to you.
Thank you very much, Jen, for the introduction. And good afternoon, fellow food scientists. Welcome to our presentation, and thank you for sharing my interest and passion for developing novel products using the ever wider and widening range of protein ingredients as a functional backbone. For our presentation today, I have a little agenda here. We'll first set the stage by evaluating the alternative protein market, which has been diversifying over the last few years to include more and more ingredient options. Then we'll jump right into the topic of the day. We'll review the different protein functionality methods and how they can be used in product development for protein ingredient selection and qualification. Then we'll discuss protein roles and functionalities in a variety of food products. We'll walk through a number of examples showing how these tests have been used in the past, working with different companies, both ingredient suppliers and CPGs. And we'll wrap up the presentation with two specific product development case studies, a coffee creamer and a high protein ready to drink beverage. Let's first set the stage by discussing the rationale and size of opportunities, reviewing the market for high protein ingredients and products. The high protein trend continues to be significant for consumers. It's a crucial part of how people think about food, and it's tied into health goals, weight management, and functional nutrition. As consumers continue to look for products that work with their lifestyle, demand for high protein will continue to grow, and the global market is projected to reach about 86 billion by 2028. The US market size is about a third of that. We're all familiar with traditional animal proteins, and those are still the biggest part of the market. Plant-based proteins have become mainstream over the last 10 to 15 years and have gained traction with consumers across the dietary spectrum. The many factors contributing to the rise in popularity of plant proteins, from sustainability, environmental concerns, and animal welfare, have also boosted the more novel class of proteins, often referred to as designer proteins. These are more and more popular and emerging from fermented proteins and animal proteins obtained from bioengineered microbes and cultured meat. So as I said, these ingredients and products have risen in popularity over the last 5 to 10 years. They include precision fermentation proteins, which are often labeled animal-free. It's now possible to buy products containing whey protein or casein that has been produced using fermentation processes. These proteins are identical in structure to those found in cow's milk and provide the same nutritional benefits alongside sustainability and ethical animal welfare advantages. All right, the goal of this slide here is to deliver a quick state of the industry review. The alternative food space has been growing and diversifying over the last 3 to 5 years. Plant-based has been a strong trend for over a decade, and the growth in this space has slowed down. Some of it is due to the economic environment. Higher grocery costs have put pressure on sales of plant-based products, which are still not at parity with their animal counterparts in terms of price. At the same time, the investment environment fueling innovation in the industry has tightened over the last 2 to 3 years due to the higher interest rates, leading to an almost tenfold decrease in investments compared to 2021, which was the peak year in terms of investment size in the area. Plant-based is still a growing trend globally, but sales in the US have slowed down by about 4 to 5% in 2024. However, diversified companies continued to establish partnerships to launch new products and expand their production capacity. Danone converted a conventional yogurt facility to plant-based yogurt production. Lactalis Canada reopened the former dairy plant as a plant-based milk facility. Kraft Heinz introduced plant-based hot dogs, sausages, and a joint venture with Notco. And Unilever and Nestle also launched plant-based meat products in Europe and Latin America. Another area of the alternative protein space is cultivated meat, also known as lab-grown or cultured meat. This is an emerging field, just over a decade old. Few products have made it to market. US and Singapore are the first two countries to sell these products, but more is being done in Hong Kong and Israel. Things are moving quickly. However, cultivated meat faces a set of difficult challenges: early stage funding constraints, technical and cost hurdles, and the lack of regulatory clarity. It's seen by companies and governments as a tool to improve resilience of food supply. And given the growing global demand for meat, which is predicted to rise by over 50% worldwide by 2050, this market is here to stay. JBS, Tyson, Cargill, Nestle, and Danone are investing in the space. Another very active area of the alternative protein space is fermentation technology. This is a technology that's gaining more and more ground in alternative proteins production. It offers a powerful, already established way to diversify the food supply. There's a rising enthusiasm for the field, which is noted because it's the only alternative protein space with growing investment year on year, even in the current economic climate. About 40% more funds were raised in 2024 than in 2023. There are three technologies under this fermentation umbrella. We have the traditional fermentation, think tempeh, cheese, yogurt, bread, and beer. There's biomass fermentation, which takes advantage of the high protein content and fast growth of microorganisms to produce large quantities of protein efficiently. This technology offers the greatest opportunity to produce protein at scale. Microorganisms grow very quickly, often doubling their weight in just a few hours. Yeast, filamentous fungi, and microalgae have been used in biomass products. The other technology is precision fermentation. This turns the microbes into cell factories, producing high-value ingredients like proteins, but also fats, vitamins, enzymes, and natural pigments. So why does this matter? Why does this impact the way we look at protein functionality? Well, we thought a few years ago that we had a lot of options when choosing proteins. But nowadays, there's even more. The diversity of ingredients is still expanding due to a few trends. Suppliers are continuing to innovate in raw material selection and protein sourcing, with crops being bred for varieties with high protein content and functionality. In 2024, Faba Protein has been having a moment. Roquette, Bungie, and Wide Open Agriculture have launched new Faba Protein isolates. Suppliers continue working on optimizing ingredients, building facilities, and specialized equipment for protein fractionation and functionalization, or evolving the manufacturing process to improve efficiency, yields, or sensory characteristics. Also, new precision fermentation enabled products such as whey protein, casein, ovalbumin, myoglobulin are being developed with great efficiency and short turnaround times. These products are similar in primary structure and nutritional composition to those found in animal products, but may have different functionality based on their tertiary structure and assembly mechanism. Best example for this is casein micelles. Precision fermentation has been used to date to produce individual caseins, but there's still ongoing research on developing or identifying the environmental factors that lead to the self-assembly of the micelle, which is a complex macromolecule made up of these four caseins and calcium phosphate. This micelle macromolecule is critical to functionalities involved in cheese and yogurt production. Okay, in the next section of the presentation, we'll go through the protein functionality testing toolkit overview with examples of use practically, and later on case studies and examples. Protein functionality testing can be used to characterize an ingredient's performance, basically establishing the functionality fingerprint of a protein ingredient. This information can provide important insight to product developers. For example, we test solubility as a precursor to other core functionalities. If a protein is water soluble, it will be able to work by stabilizing interfaces like emulsions or foams, stabilizing suspension by physical interference, distributing the electrical charge at the surface of the proteins, or building viscosity. Solubility can be measured at different pH points and would allow us to identify the isoelectric pH of a protein. A product's heat stability can be assessed by applying controlled heat experiments and characterizing the impact on protein fractions. We can measure the water or oil holding capacity of an ingredient or its emulsifying properties. We can determine how many milliliters of oil can be stabilized by a gram of protein, or characterize the emulsion stability in a system. Additional tests can be used to characterize emulsion stability in applications, such as particle size distribution or stress test via centrifugation. Foaming properties can also be characterized using a standardized method to prepare a foam, measure its expansion and stability. As mentioned before, zeta potential can be used to establish the electrical charge of a protein. Larger electrical charge is an indicator of high colloidal stability, providing interparticle repulsion for stable dispersions. Lastly, SDS page is an interesting method. We use it often in root cause investigations to establish protein integrity and stability to degradation induced by age, enzymatic action, or heat and other processing factors. Understanding an ingredient's functionality has product development implications. Certain performance indicators are desirable in some applications and help an ingredient perform in applications and unit operations. Others are less so. Each ingredient has its own potential, and our role as product developers is to select the best tool for the job, the best protein for the right application. For example, acid casein is a well-known ingredient, has been around for a long time. It's a protein ingredient with low solubility, as it's produced by acidification of casein to a curd, which is then dried and milled to a fine powder. This powder doesn't hydrate, solubilize, or displays much functionality at all. But that doesn't mean it doesn't have its uses. It's the perfect inclusion. It's not going to build viscosity. It will not heat nature or gel. It will not be gritty if you mill it to a low enough particle size. And it will not case harden when incorporated in a protein bar like whey protein does. A protein with low heat stability may not be the best choice if you're developing an RTD beverage, which will need to be UHT processed, but may be the perfect candidate if you're developing an egg replacer, which needs to coagulate and texturize when heated. Foaming also may not be desirable in certain process operations like filling, mixing, but is critical for whipped applications and cakes. Again, it's our job as product developers to showcase the ingredient in the best application that takes advantage of its strengths and minimizes its weakness, or to select the ingredient that best fits the rigor of an application or its process flow and unit operations. So I've been building up to this slide for a while now. There are different ways to use protein functionality testing, but the two more distinct approaches we've seen in our work have been pretty well defined by the type of company we're working with. Most of our work is with CPGs, focusing on product development and scale up, but about a third of our projects are with ingredient suppliers. When working with an ingredient supplier, our approach is ingredient-centric. We use functionality testing as part of the ingredient development process. A quick example, we were working with a company developing an upcycled ingredient, which was to be used in a high protein RTD application. So we used high solubility and heat stability testing as the more important functionalities, testing it repeatedly on different process variables iteratively as part of the ingredient's development process. If the ingredient is mature and is in the commercial stage, we can use the full functionality toolkit and characterize its functionality fingerprint, then identify the best application opportunities. We summarize the functionality data and present it to a diverse internal team of product developers with different backgrounds. in application development, scale-up and process development, microbiology and food safety, culinary, and build on their experience to identify the applications in which the product would perform best. We brainstorm a number of ideas, incorporating the ingredients' advantages, whether they're sustainability, whether it solves a technical hurdle, cost, etc., and rank the best, most promising applications. The supplier can then target market leaders in those product areas as part of their sales efforts, unlocking the ingredients' revenue potential. Other ways that we support the sales team of our clients is by building data sheets and technical bulletins, often comparing the plant-based ingredients to the animal-based gold standards. Or we can use the test to understand an ingredient's loss of functionality during shelf life and suggest in-use adjustments that can be made to mitigate this. For CPGs, the approach is more application-centric. If the ingredient has a product idea, then we identify the core functionalities for that application and test them for a number of ingredients. Initially, the list of potential ingredients is narrowed down after applying any other criteria useful to the project, like raw material source, cost, allergenicity, consumer perception, etc. This way we can narrow down the field and then efficiently screen through a large number of ingredients using functionality tests and come up with a short list of high performers, which can then be used to streamline the development process. The more thorough approach when working with CPGs, though, is to build a database of fully characterized ingredients. This database can then be sorted by target application, by weighing the critical functionalities only, and ranking the best performers. So from the same database, by weighing different functionalities, you would get a top 5 for RTD beverages by weighing the highest solubility and heat stability and emulsion properties. Or you can get another top 5 for bakery applications by ranking water holding capacity, emulsifying and structure building or gelation potential. All this can be done by a quick ranking exercise from the same database, and additional fields can be expanded in the database to include criteria like cost. This would streamline any cost improvement projects by enabling informed ingredient substitutions while maintaining ingredient performance. We like to say that using protein functionality is the performance-driven approach to product development. The traditional approach involves a lot of trial and error, a lot of substitutions based on one-on-one replacements or nutritional matching, without accounting for differences in functionality. It has been described as a hunt and peck approach to development, where you may or may not land on a working solution, and pilot plant trials can be quite risky. It's inefficient, time-consuming, linear, and less predictable. The performance-driven approach incorporates functionality testing as previously described, and is data-driven, efficient, more streamlined, and builds IP. It helps de-risk trials, improve speed to market, and builds confidence for big decisions like what market segment should we go after next, or how big of a formulation hurdle will this be? All right, in the next few slides, we'll discuss examples of using specific tests. The first 2 test methods are solubility and heat stability. To test solubility, we prepare a solution of known concentration. We allow the protein to hydrate and equilibrate, and then we centrifuge the solution to separate the insoluble particles into a pellet. Then the supernatant is separated and tested for protein content, which allows us to quantify the proportion of protein that is in solution. The solubility index can be calculated with the formula presented here. Basically, the proportion of protein that is solubilized as reported to the original total protein content. The heat stability assessment can be tailored to the more relevant process for each product. We can do simulations of HTST, UHT processes, or any other custom process. If a product is an acidified beverage, then we can pasteurize it, HTST simulation. If the product is a low acid beverage, which must be shelf stable, we can use a UHT simulation. The simulated heat treatment can be performed under controlled conditions, And after the treatment, the same sequence of operation used in solubility testing, meaning centrifugation, separation of supernatant, and testing it, will allow us to identify or determine the proportion of soluble proteins that are heat stable or remain in solution after the heat treatment. We also use the process simulations as a prerequisite before pilot scale processing using microthermics to improve first pass efficiency of pilot plant trials. You can see here in the pictures that it helps prevent some of these undesirable outcomes. You can quickly and efficiently test the viability of more complex formulations that include buffers, hydrocolloids, or other stabilizers alongside the proteins. As mentioned before, the method is flexible in terms of temperature and time exposure, and it's quite cost effective. 1 man-day of benchtop screening can save 3 days of pilot plant time and up to 11 days of manpower, which you'd need to interrupt your production and start cleaning the microthermics if you get in any kind of situations like the ones pictured here. Emulsifying properties can be tested a few different ways. One good comparative method is the emulsion capacity, which provides a measure of the protein ingredient's capability to stabilize oil. We continuously add oil to a system under high shear until we achieve an inversion from an oil in water emulsion to a water and oil emulsion. That's the upper limit of the protein's oil load and can be reported as the volume of oil stabilized by a gram of protein. Other methods can be used to characterize model systems or in actual applications to understand the protein stability and emulsion stability by analyzing its droplet distribution as well as its resistance to separation or tendency to aggregate. So how can these tests be used from a practical standpoint? Particle size is a very powerful tool to predict long-term stability of emulsions. It can be used to screen through emulsifiers based on desired performance at target pH and oil load. It can help in process development to identify the right homogenization pressures that result in the smallest average particle size. And also success criteria of particle size distributions can include the nature of the distribution. Unimodal versus bimodal, for example. Unimodal is preferred as it's a tighter distribution with fewer classes that can tend to separate more. Other techniques have been developed which characterize a product's sedimentation or separation behavior. By correlating the G-force used in centrifugation and the fat depletion in bottom layers of a product during centrifugation, you can predict separation behavior over months of shelf life. In the example presented here, we've tested a fresh product at time 0 after production, calculated a creaming rate or a separation index, and then used that to predict how much separation we'd see 8 to 9 months later. We kept the product under observation, tested again after 8 to 9 months, and the separation index was very close to that predicted at time 0. So it's a nice, reliable method that can be used in product development to directionally move the stability challenge towards a finished product. Another widely used test is foaming behavior. We prepare a foam under controlled conditions and determine the foam expansion, measured in percentage, and the foam stability, or half-life, is the amount of time needed for 50% of the liquid in the foam to drain out of it. Protein is key in stabilizing foams, and it's a critical functionality for products like barista blends, for example. In these pictures, we can see differences in foam performance in a coffee application for an oat milk beverage compared to a dairy milk gold standard. All right, the last test we'll review today is SDS-PAGE. It's a well-established electrophoresis technique that allows for the qualitative analysis of protein composition and molecular weight. It can be used in different ways to assess process impact or stability for process control, especially in fermentation processes like cheese ripening and aging, or in troubleshooting. Recently, we were working with a client who incorporated an enzymatic treatment in their process flow. Enzymes were used to break down cell walls and improve extraction efficiency. With a new lot of enzymes, they were noticing higher protein extraction and lower stability of the finished product. By using SDS page, we found that the different protein fractions were being extracted from the substrate initially, and due to a slightly different activity of the enzyme blend. These new fractions were less heat stable than the original fractions, and were precipitating out, causing processing issues. The client was able to work with their enzyme supplier and get things back on track once they had this information and hypothesis. All right, the next section of the presentation will be discussing a couple of case studies selected based on relevance to market. So looking at market data, sales data from 2024, we see that two particular products are doing quite well over the last 3 years or so. Creamer has decreased a little bit in 2024, but over 3 years, it increased by 30%. Ready-to-drink beverages have continued to increase, even in the a tougher economic environment we're experiencing. So the first case study deals with plant-based coffee creamer. And plant-based coffee creamers are one of the more dynamic alternative product categories, with a growth of about 31% in the 2021 to 2024 period. Plant-based creamers benefit from two consumer trends, as consumers seek sources of healthier fats and oils, but also to incorporate more plant proteins into their diet. A coffee creamer has several functions in use. It provides beverage whitening, which can be tested using an LAB colorimeter, mouthfeel, and flavor release. All these functions are closely related to the quality of the emulsion created in the creamer. So how do we develop a stable creamer? We can choose semi-solid fats, such as coconut or palm oil, which at room temperature will be less likely to coalesce. We can ensure good emulsion stability by stabilizing the oil-water interface via protein absorption through homogenization. Homogenization provides shear to create a fine emulsion, but the whitening power of the creamer depends on particle size distribution of the fat droplets. Only oil droplets in the 1 to 10 microns range lead to the desired coffee whitening effect. Droplets that are too fine have a blue or grayish hue, while larger droplets become visible as fat smear or sheen of the surface of the beverage. The ideal plant protein for this application should have high solubility, high heat stability, and high emulsifying activity. The next case study is a little different, as it builds on using a blend of two proteins, a dairy protein and a plant protein. These blends have been used more often recently as cost-saving strategies, especially in a current economic environment, and a way to unlock synergistic benefits of blends. It's a critical strategy when trying to develop high-protein beverages, in this case above 25 grams per 8-ounce serving. In the development of this application, we used a variety of methods in the testing toolkit. Heat stability was used to identify the critical concentration for gelation of one of the proteins, the soy protein. Viscosity and flow index were used to characterize the different blends, different solutions for best stability and processability. We were looking for a flow behavior that was as close to Newtonian flow as possible. Zeta potential analysis was used to get an early read on storage stability. Particle size analysis was used to determine potential aggregation and protein instability. And native page, a modification of the SDS page method, was used to investigate whether any cross-linking between the different protein types, the casein and the soy protein, was happening. And centrifugal analysis was used to assess physical stability to sedimentation, although when one of these systems was prone to sedimentation, it was very quickly apparent. All right, the blended system contains micellar casein and soy protein, and each of them individually are challenging to use at these higher concentrations. Micellar casein is highly heat stable, but has low solubility. And especially at these concentrations and after heat treatment, has the tendency to sediment during storage. Heat treatment of casein only, micellar casein only systems led to calcium phosphate depositing on the surface of the micelles and blocking the charges that keeps them in suspension by preventing them from getting too close to each other, steric exclusion, and weighing the casein micelles down, so they were more prone to sedimentation. On the other hand, using soy protein at a high concentration of 10% puts it over the critical concentration of gelation, which is around 7.5%. Even at concentrations that are lower than the critical concentration, the viscosity was very high, and it had a pronounced shear thinning behavior, which is less than desirable for pumping and transfer operations. Neither of these proteins, if used on their own, could unlock the 25 grams protein per 8-ounce application in the system. This data presented here is showing different impact of concentration on viscosity, and the different flow behaviors experienced before and after heat treatments. As we can see in this picture, micellar casein on its own, 5 or 10% protein, quickly sedimented after heat treatment, within hours after the heat treatment. In this picture, we can see the impact of concentration and more intense heat treatments. And the higher we go in the temperature of the heat treatment, the more the protein exhibits a lower zeta potential due to that precipitation of calcium phosphate and blocking of the zeta of the charges at the surface of the micelle. This again makes it more likely to sediment out of solution. However, when you heat treat a 50-50 blend of micellar casein and soy that is used at a 10% overall concentration, the result we get is denatured soy protein and no cross links between casein and soy. We use the native page to investigate that. So basically they act as two different systems that don't interfere with each other. The unfolded linear glycinin chains stabilize the suspension, preventing the micelles from sedimenting. And the other benefit they have is that these linear chains have a lubricating effect. So when flow starts, it helps those casein micelles slide and lead to a Newtonian flow behavior and a much lower, 75% lower viscosity than before the heat treatment. Both proteins carry negative charges, and due to steric repulsions, they keep the suspension stable during storage. So this formulation, in the absence of any other stabilizers, just by using a blend that shows a synergistic effect, allowed us to get to 25 grams per protein per 8 ounces, and could potentially be increased in concentration as long as the soy protein level is not increased past the critical concentration point of 7.5%. All right, that was a lot of information, and we'll switch topics a little bit. Basically, we'll review, what are some of the typical programs, types of projects that rely or leverage protein functionality. We've touched on some of these, but we worked a lot with established CPGs that are diversifying into plant-based products or redesigning their products and processes to adapt to the use of plant-based ingredients. In many cases, people new to the industry will try to use the same process that is typically used in animal products like cheese making, the reliance on rennet for structure formation. The rennet will not help much when you switch to a plant-based. So in that case, you really need to redesign your ingredient deck as well as the process and create structure using another mechanism, either heat gelation or use of starches and other structure forming ingredients. We also work with ingredient suppliers looking to understand how their ingredients change after their process is evolved as part of their development or optimization process. best example and timely, with so much activity in the fermentation space. A lot of optimizations involves, perfecting the titer, getting as much protein in the continuous phase in the broth as you can. All those process improvements, you want to know if that process optimization results in a different functionality or an impact on your ingredient. And one of the advantages that we bring to the table working with us is the fact that we have a wide industry perspective, and this helps prevent blind spots. So even an established plant-based market player that has experience in the plant-based field, but they're looking to expand into a new market, would benefit from an outside view. Let's say they have a star ingredient that has worked really well in the past for them. They developed a high protein beverage, RTD, and the hydrolyzed protein with high solubility and high heat stability was a great choice. If they branch out just lightly into a meal replacer or include a fat component into that system, that ingredient choice will no longer work. They will quickly learn that the emulsion will fail if you use a hydrolyzed product. So you'll need to get the emulsion functionality some other way, either by getting a new protein or using another ingredient. Other types of projects that we see a lot are troubleshooting or feasibility assessments. And it takes a more customized approach, whether by using model systems to test feasibility or viability, or carrying out root cause investigations. But the functionality tests come in handy in those projects as well. Looking at the future, we see more potential for a data-driven approach to product development. As more and more companies are looking to diversify their food supply, whether it is to protect the supply chain against climate extremes, disease outbreaks, conflicts, and market volatility, the food ingredient market will continue to be a dynamic area. Product developers will continue to need tools to qualify and select novel ingredients for targeted applications. And these ingredients are no longer just proteins. A range of precision fermentation ingredients are emerging: fats, complex carbohydrates. Also, another class of ingredients getting more and more popular and launched on the market are biomass ingredients, like filamentous fungi or yeasts. These present specific differentiated challenges related to cell morphology and behavior during typical food unit operations. We'll be branching out into specialty testing of these novel ingredients as well as standardized tests or custom-built model systems to continue supporting our clients. All right, thank you so much for your attention. Jen, do we have any questions from the audience?
Yes, it looks like we have a couple. So the first question is, going back to the fermentation with biomass, are there any potential drawbacks to fermentation with biomass, when looking at protein functionality?
Yeah. Biomass ingredients have distinct advantages related to cost, getting to market quickly, sometimes high protein contents, or quite diverse nutritional profile. The main challenges that come when using them are that you have to use the whole cell. So whether it's a fungi or a yeast, these ingredients are not fractionated or processed further than separation washing of those cells. So the biomass has to be used entirely as an ingredient in applications. And sometimes it can have a functionality that is due to protein or other fractions, like carbohydrates or fibers can drive functionality, and less the protein, which sometimes is caught in the cell membrane and doesn't solubilize very easily. So the functionality that then comes from the other parts of the components in the cell or the cell itself, its size, its zeta potential, its behavior, its hydration. So yeah, the approach is much more customizable. You have to take each ingredient as its own system and understand how to use it. In a way, it's very close to that ingredient supplier approach, where you study the ingredient, try to understand it, and find the application where it can do the best work for you.
All right, perfect. Thank you. Another question. When evaluating different proteins using the attribute performance approach, can you continue to add on new novel proteins using the similar evaluation?
Yes. So either if you're working, let's say you're working on an application and you're testing 10 proteins initially, but then you find out that there is a couple more that the supplier is shipping you, and you'd like to understand how they behave, you can always add more to that database. Or if you're purposely going for building a database, nothing prevents you from adding new ingredients and using that database to sort through and see which products are shortlisted for different applications. It's a very useful tool.
Perfect. All right. We have another question. What are the most effective preservatives to avoid denaturation through pasteurization in ready-to-drink plant protein beverages? Any thoughts on that?
Denaturation. In many cases, plant-based proteins exhibit a much higher heat stability than animal proteins. A lot of times we see that heat treatment actually drives up the solubility of the protein in the system, probably because of the high heat treatment will break down the cell walls and get more protein out there. And in that case, a lot of the models or the methods set up for animal proteins or dairy proteins, even what we originally were using with a heat stability index, where 100% would be the same amount of protein that was soluble initially is still soluble after heat treatment. In the case of plant proteins, you get things that are above 100% because more protein gets solubilized by the heat treatment. So with plant-based, we've seen less of that heat stability issues, unless, except for certain cases in which you do see it. In those cases, I would say using blends is the way to go. So think about the soy protein example I was giving. It has a critical concentration, after which it starts causing issues. If it just denatures and unfolds and doesn't form an agglomerate, then it can be stabilized with suspension aids or anything like that. But if it starts forming agglomerates or cross-linking, then it gives you a harder time in terms of stability. So the best way is to just start using a blend and stabilizing it that way.
Okay, perfect. Well, it looks like one more question. Have you run into a scenario where you are not able to achieve foam stability needed for the product, since that's such a key piece?
Yeah. No, that happens, especially if your protein, let's say, has good foaming ability, expands and traps air well, but then because of, let's say, a lower viscosity of the system, it tends to drain out very quickly. The way we've stabilized in the past was to use hydrocolloids to increase the viscosity of that continuous phase. That way, the foam, the air liquid layer, that doesn't drain as quickly because of the higher viscosity. So your product is stable for a longer time.
Perfect. Well, it looks like we've addressed quite a few questions in the chat. For other questions, we definitely can follow up following today's presentation. Thank you so much, Cosmin. It was an excellent presentation, lots of really great information. I just want to say thank you to everyone who's attended. Definitely please feel free to reach out to us with any questions, and we would be happy to connect further to discuss this very important topic in product development. So this now will conclude today's presentation. Have a wonderful day.
Have a great day. Thank you.